Hi, everyone. Welcome back for Henry's second and final hour. So, Henry?
Great. Okay, so to pick up where we left off, I guess we talked about this motivating application. We talked about sketch verification schemes. And then in the rest of this hour, I'll talk about zero-knowledge proofs on secret shared data. And then I'll try to cover as many applications as I can. And I absolutely will not cover everything that I would like to cover, but some of the other stuff I put in the lecture notes that Benny will post online. So good. So let me tell you now what a zero-knowledge proof on secret shared data is. And how it's relevant to the applications that we've been talking about so far, and then I'll talk about other applications in a moment. So this is, you should think of this as like, sort of like these sketch verification schemes. With a proof. And who provides the proof? Well, the proof comes from the client. So the client, the servers are not only going to check some property of the input that the client has provided, but the client is going to provide some extra information that's going to help the servers check this proof. And I'll try to explain why this is interesting and why we might actually get more powerful things out of this zero-knowledge proofs on secret shared data than we can with sketching. So the picture that you should have in mind is there's a prover, where you can think of this as the client, and some verifiers that you can think of as the servers. So there's one verifier here, there's another verifier. I'm just going to draw it with two for space reasons, but there could be more. And the prover has some shares of an input. So again, say this is a dimension n vector. And each of the verifiers will have one piece of the input. So as with the analytics application, you know, verifier server A has piece XA and server B has piece XB. But the difference in kind of syntax here is that now the client is actually going to send, in addition to its input, will send the verifiers some kind of a proof. And the proof is also going to be a vector of field elements, so call it pi A and pi B. And then the verifiers will kind of chat amongst themselves, have some communication, and then either accept or reject the proof. So why this is relevant to what we were just talking about? Well, the prover's goal here is going to be convince the verifiers that in the specific case of secret shared data, that the sum of their inputs is in some language that's, I don't know, a subset of the all dimension n vectors in this field. So this could be, you know, to relate it back to what we were just talking about, this could be convincing the verifiers that the sum of their inputs is a vector of all zeros with a single one. It turns out in that case, you know, the sketch verification schemes show that you don't need a proof at all. The verifiers can just test that property directly. But in other cases, like ones I'll mention in a second, a proof is actually necessary, or it seems to be necessary. So as in, but the kind of goals here are quite similar. So as in sketch verification schemes, we still want these sort of the usual three properties. So completeness and soundness and some kind of privacy or zero knowledge. Again, I'll just stick to honest verifier zero knowledge. So I'll try to sketch what these mean. So completeness here is meaning that you know, for all XA and XB that whose sum is in this language, the probability when you run this protocol between the prover and the verifier A and the verifier B on these inputs XA, XB, the probability that the honest verifiers accept should be 1. And soundness is similar to sort of the usual notion of soundness for all XA and XB whose sum is not in the language. I guess, and for all provers, for all malicious provers, the probability that these honest verifiers will accept should be something small. You can think of this as, say, 1 over the size of the field, something like that. And the privacy property is very similar to what we saw for the sketch verification scheme. It's kind of like there should be a simulator such that for all inputs that are in this language, the view of one of the servers, or each of the server, so the view of server A in this protocol should look like the output of this simulator. So basically saying that each one of the servers independently learns nothing about this secret shared value X, apart from the fact that it's in the language. So, and again, this notation just means running this three-party protocol where verifier A's input is XA and verifier B's input is XB. And I guess the prover's input is both of these things. Any questions about the syntax before I go on? No? Okay. No? Great. Yeah, at this point, I've had like 8 cups of coffee this morning. So if I start going faster, tell me to slow down. It's good. So, okay, so let me give you some useful results to know about these proofs, zero knowledge proofs on secret shared data. So the one, I guess I'll state one more formally and one less formally. So this is from this 2019 crypto paper with Alette Boyle, Dan Bonnet, Alette Boyle, me, Niv Gabor, and Yuval Shai. So this is, if you want to look at the paper, it's 2019 paper. And the theorem says that if this language that we care about, so the set of vectors that are kind of the good vectors, is computable by an arithmetic circuit over F. So this is just a circuit that uses addition and multiplication gates, say mod P, of size C. So if the language has circuits that are not too big, then there is, say, a zero knowledge proof on secret shared data, for the same language with communication cost as follows. So the prover to verifier cost or client to server cost is linear in the size of the circuit. And the verifier to verifier cost or server to server cost is constant. And these costs I'm measuring in elements of the field F. Yeah, so this is a useful thing to know. So a couple of other points. So points about this. So I guess one thing is that this is an unconditional result. So it doesn't require one-way functions. It doesn't require any kind of assumptions. This is just an information theoretic statement. And it turns out to be, for designing these protocols, is super useful because it says that whatever the client needs to prove to the servers about its input, you can do it as long as what it's proving is not too complicated in terms of circuit complexity. And I'll give one concrete example of this. But this ends up being a useful tool. What's even more useful is that if right like this, so if the prover and verifiers can interact and the language is simple, relatively simple, or structured. So for example, this circuit C that recognizes that computes the language has degree 2, so low degree. Then the communication cost falls to something like log size of circuit field elements. So if the client needs to prove something to the servers and the thing it needs to prove about its input is relatively low degree, then it takes actually very, very little communication between the clients and the servers to do this. So the kind of interactive setting is, I described the proofer as sending kind of one proof string to each server, but you could imagine the client sends a proof string and then the verifiers send a message and the client send a proof string and the verifiers send a message, and you kind of do a bunch of this kind of interaction. In that case, when your circuit is simple, you can get much, much better communication. So I'll mention this sort of sublinear proofs end up having lots of applications. I'll mention, I hope I'll have time to mention some of them, to say malicious secure multi-party computation ends up being super useful. Yeah, maybe, are there any questions about this so far?
Yeah, there is one question. If the verifiers need to interact with each other, why not just run an MPC between the verifiers to decide whether X lies in the language or not?
Great question. Great question. So there's a couple of ways to answer that question. I think the easiest way to answer the question is if you look down here, if you actually ran an MPC to check this predicate, the MPC would probably have kind of linear in the circuit size amount of communication, because typically in MPC protocols, you have to communicate kind of some bits for each gate in the circuit. And here that would be C communication, whereas here we're getting log C communication. So you're getting an exponential improvement. Even up here, it ends up being useful because the sort of concrete efficiency of the protocol ends up being better. It ends up being a simpler protocol to achieve the same properties. But that's a great question. Yeah. Any other ones in the queue?
How does this compare with ZK for NP languages?
Yeah. So where you have just one prover and one verifier. Is this?
I assume so. It wasn't mentioned.
Yeah. So I guess in the sort of traditional setting of zero-knowledge proofs, there's only one verifier, and the verifier has the whole input, and the prover is trying to convince something to the verifier. I guess the difference here is a bunch of things. So here we're interested kind of in information theoretic statements, but also where each verifier only sees part of the input that's being proved about. So normally in zero knowledge proof, I give you a graph, you the verifier, I give the verifier a graph, and then I'm going to try to convince it that some property about this, that the graph is three colorable or something. Whereas here, each verifier only actually would see part of the graph. So it's a very different kind of setting, and ends up being, different protocols and different applications. Hope but it is very, very similar in spirit, I guess. So cool. So the full result here, I won't be able to have time to prove either of these things kind of completely. But instead, I wanted to give you kind of one special case that I hope gives a flavor of the results and the techniques that end up being used, and also why these things end up being actually relatively simple. So cool. So let me try to do that. And the example I used is actually a practical example that people have implemented that's used in real systems. So the example I'll use is checking that a secret shared vector has kind of all 0, 1 elements in a big field. So we're working mod P, where P is an 80-bit prime or something, and each server has a secret sharing of a vector, and the servers want to check that each component of this vector is a secret sharing of a 0 or a 1, not a big value or a negative value or something funny like that. So as an example application, if you want something to think about, you can think about, say, I don't know, Mozilla, there's lots and lots of applications of this, but Mozilla wants to know, say, which websites in the top, Alexa top 10,000 use Flash. Adobe Flash, which was a web technology that's kind of going out the door. Why do they care about this? Well, if a lot of the top 10,000 websites are using Flash, then maybe they still have to support it for a while longer. Or if there's only a handful of websites using Flash, then they need to go talk to those people and convince them to modernize their websites. But this is kind of a question that a browser vendor will want to know. And what a client, how that would work in this kind of private analytics setting is that the client has this vector. And each component of this vector is a 1 or a 0. So this is, something like this, where the ith component is a 1 if the ith, website, served Flash content to the client. Yeah. So valid inputs in each of these components are zeros and ones. Does this make sense? Rahul, are you good? All right, cool. So, right, so what's going to happen is the client now is going to send a proof to each of these servers, server A and server B, and the servers are going to interact and then accept or reject. And the servers are trying to check whether their shares, so XA and XB, when you add them up, are kind of this in this language. So it looks very, very, very similar is the sketch verification stuff we saw already, except with the addition of the proof strings that the client has to send. You could ask, is it necessary? Why can't we just be more clever and cook up a sketch verification scheme for this language? And it turns out that in some settings, you can actually prove that there are languages that kind of require either a lot of communication between the servers to check, or some communication between the clients and a lot of communication between the clients and the servers to check. So in some settings, you can actually show that this sort of sketching alone without any interaction with the client is kind of not sufficient if you want a sublinear amount of communication between the servers. So I'm going to try to sketch the protocol that actually does this. This may be a little bit ambitious, but I hope that even if the whole thing doesn't make sense, that you get kind of a flavor of what's going on. But I would feel bad if I didn't at least try to give you some of the technical detail. So the idea here is as follows. So we're going to let the client's input, the secret shared vector, be this vector x1 up to xn. And we're going to define 3 polynomials. Over this field. And the polynomials are going to be that's for all points in, this is a set 1 to n. The first polynomial is going to satisfy f of I being equal to xi, so the ith input value. And g of I, the next polynomial, is going to be xi minus 1. And h is going to be f times g. Yep. So the first polynomial is f, the second polynomial is g, the third polynomial is h, and they have this super simple structure. So these guys, I guess, are going to have degree. If we pick the lowest degree polynomial that satisfies these constraints, is going to have something like degree n, and this guy is going to have roughly twice the degree because we're taking the product of 2 degree n polynomials, so something like degree 2n minus 1. And I'm abusing notation here only slightly in that I'm calling these points in the finite field 1 to n. So forgive me for that. Okay, so why is this kind of the right thing to do? Why is this the right idea? So what you can observe is that if x is in this language of, I'll write it up here. So this language is the kind of 0, 1 strings. If x is in this language, then for all I in 1 to n, h of I is equal to 0. So why is that? Well, h of I is equal to f of I times g of I, which is equal to xi times xi minus 1. And if x is 0 or 1, that should be 0. And the final result. Yeah. So just testing whether x is 0 or 1. Okay, so that's first thing to notice. The second thing to notice is that if x is not in the language, then there exists some I in 1 to n, such that h of I is not equal to 0. Well, by basically exactly the same argument. So pick the I, if x is not in the language, then there's some I for which x I times xi minus 1 is not equal to 0. And then h of I can't be equal to 0. Yeah, so that's the second, basically the same argument. Okay, so this is almost all kind of the setup that we need. The last key facts that probably won't be obvious, but that are not so difficult to show, is that if the servers are given shares of x, of this input x, they can compute shares of f of r and g of r for any random points or any points in the field without communicating. And the reason for that is that if you look at how these polynomials are defined, f of r for any r that the servers pick is actually just a linear function of x. And so the servers can compute linear functions on secret shared data without communicating, and therefore they can compute shares of kind of the evaluations of these polynomials without communicating. So this requires just kind of writing down what the equations are for polynomial interpolation and evaluation and seeing that they're actually linear functions of x when the polynomials are defined like this. That's key fact number 1. And key fact number 2 is given shares of the coefficients of this polynomial h, they can compute shares of h of r, again, for any r and f, any r in the field, again, without communicating. And this is also just the fact that that evaluating a polynomial at a public point is just a linear function of the coefficients of the polynomial. The fact that we're using a linear secret sharing scheme is super helpful here. Any questions about this? I can't tell how much chaos is in the chat, so I'm going to rely on you to let me know. Okay. So good. Okay, so this is all seeming a bit abstract, but let me try to explain now how we use this to check the thing that we wanted to check. So let's see the recipe here, and this is a bit only lightly simplified, is as follows. So the client in this protocol computes this polynomial h and sends shares of its coefficients to the servers. So that's the proof. This is the proof. This is the proof is shares of the coefficients of this polynomial h. And this requires something like n field elements. Next is the servers check that h of I equals 0 for all I in 1 to n. So how do they do this efficiently? Well, I just, the second fact here was that if you're given shares of the coefficients of this polynomial h, they can compute shares of h evaluated at whatever point that they want. So the servers just kind of compute locally without communicating. They compute shares of h1 up to hn, and then they take a random linear combination of these and check that it's equal to 0. So this is kind of a randomized test with like one field element worth of communication that h of 1 up to h of n is 0 everywhere. Yeah, so that's the second thing that the servers do. And the third thing is they kind of need to tie their input x to the values of this polynomial h. So what the servers do then in the last step is check that f times g equals h. So remember, f and g are these polynomials that are defined by the client's input, and h is the proof that the client sent. So if f and g are kind of computed from the client's input, and h is also correctly computed as f times g, then these two facts tell us that basically if h of I is 0 everywhere, then the client's input is in the language that we care about. So the last step here, and then I'll try to kind of go back and explain why this works, is they use a randomized polynomial identity test for this. So the servers choose random r in the field, and they check that f of r times g of r equals h of r, and this also only requires kind of a constant amount of communication by the fact that polynomial evaluation and interpolation like this can be done for the most part locally. Yeah, and this is you can do this with a constant size MPC, or you can even avoid using any kind of MPC. So yeah, so the servers accept if steps 2 and 3 accept. Yeah, so the servers are checking this thing here and this thing here. So in some sense, it's a very simple protocol. In some sense, it's maybe even if you don't have total intuition about how it works, you can be convinced that this may not actually be so difficult to implement, right? There's no hidden scary stuff going on here. I guess the idea, again, to try to give you some intuition for what's happening, is that the client is the client is giving the servers this polynomial h. The servers derive these polynomials f and g from their own inputs, and if f times g equals h, and the output of h is good in some way, then the servers are convinced that the input is in the language that they care about. So there's kind of two steps. One is checking that this h of I is equal to 0 everywhere. That's what the servers do first. And the second is that checking that h is computed correctly. And that's the last check the servers do. And if you kind of patch all of this stuff together, you can be convinced that this protocol is simultaneously complete and sound, and can be made to satisfy this honest verifier zero knowledge notion. Okay, so I felt obligated to try to give you at least some intuition for what's going on here. The thing, I'll just summarize the communication here, is the proof to verifier communication is like n field elements each. And then the verifier to verifier communication is like, I don't know, something like 4 field elements. I haven't computed this constant exactly, but it's something like 4. And I guess the other thing to see is we didn't really use any super special properties of this language here. And in fact, by kind of changing the definition of f and g, you can make this work for not only this language, but any language recognized by a circuit with n multiplication gates in it. So this is just tweaking this protocol a little bit gives you kind of the full theorem that I promised at the beginning. Okay, so the last thing I want to say about these proofs on secret shared data, which is important for the applications, but again, I'm not going to have time to prove, is that when the language is structured, or I should say, computed by a structured circuit, then we can reduce the proof size, or the prover to verifier communication. And I'm, again, not going to prove this. I would just want to tell you the basic idea. The basic idea, which sort of looks like the same idea that's used in some check protocols, if you've seen those. So the basic idea is say that the language on, I'll call it L of n, has a circuit of size n with, let me say circuit with n repeated subcircuits in it. So there's kind of some structure that's repeated n times in this in the circuit that recognizes this language. So actually, the circuit for checking 0, 1 to the n is of this form because you're doing xi times xi minus 1 a bunch of times. So what we do is we construct a zero knowledge proof on secret shared data, whose verifiers must compute a circuit so I'll call this circuit C of n. They have to compute the circuit C of n over 2 to check the proof. So basically checking the proof for the instance of size n requires computing the same circuit on an instance of size n over 2, and then you recursively use zero knowledge proof on secret shared data. So what does that mean? It means that the verifiers essentially ask the prover to convince them that the verifiers would have accepted this kind of next level check. So maybe I'll draw a picture to try to make it more clear. So we have the provers and the verifiers. So it's, I don't know, multiple verifiers here. The prover sends kind of the top level proof. And what the verifiers do is they send the randomness that they would have used to check this top level proof. And then they say to the prover, convince us that we would accept pi 1 if we checked it using randomness R1. Yep. So rather than checking the proof ourselves, we're going to ask you to convince us that we would have accepted the proof if we had checked it. And then the prover says, okay, here's a second proof. And the second proof is going to convince you that you would have accepted the first proof if you checked it. And then the verifiers say to the prover, okay, we're not actually going to check that proof. We're going to give you more randomness, and we're going to ask you to convince us that if we had checked the proof, we would have accepted it. And this continues, until you get to something very, very small, and the verifiers can check that themselves. And this works when the kind of checking the proof becomes easier and easier as you go down. So kind of at each level of this recursion, we need to cut the size of the problem in half. And if your circuit has the right structure, this is possible. So, okay, I'll pause for questions in 1 second, but just to sum up, there's kind of 2 tools we've talked about for protecting against misbehavior in these kind of protocols using secret sharing. So the first one is for testing simple predicates. You can use these sketch verification schemes where there's no help from the clients is needed. And if you want to test arbitrary predicates on secret shared data, you can use these zero knowledge proofs on secret shared data, which do require kind of help or a proof from the client, and but have the benefit that you can test whatever predicate you want. And the communication complexity depends on kind of how complicated of a predicate that you're talking about. So are there any questions that I should answer before I talk about applications?
There's one question. Can this be seen as a dealer-rated MPC between verifiers where the prover is acting as the dealer?
Yeah, this is a great question. So if you've seen MPC protocols, you might think of kind of a dealer as giving some inputs to the verifiers, and the verifiers are computing on the stuff from the dealer. The distinction here is that the dealer is might be dishonest, and the verifiers kind of want to compute the right thing, even if the dealer is trying to cheat them, right? Because if I'm the client in this protocol, adversarial clients, I'm trying to convince you to accept my input. And so maybe I'll give to the verifiers, instead of what I should have given them, I'll give them some cooked values and hope that they'll accept my bogus input. So this is kind of the difference from the usual setting. That make sense?
Yeah. One more question.
Mm-hmm.
What are some interesting examples of languages with this nice structure?
Yeah. Great question. So, one is say the one that I just was talking about. So if you want to check that the language is kind of the language of values in 0, 1 to the n in a big field, and what the structure looks like is you have a bunch of inputs, x1, x2 to xn, and the circuit computes multiplication of x1 with x1 minus 1, and then outputs this, and it does this a bunch of times. There's kind of a bunch of, you can think of this as like a SIMD circuit, same instruction, multiple data. And any circuit where there's kind of a repeated, I guess if you look at half of this circuit, the left half and the right half are doing exactly the same thing. And if you chop it again, you'll see that each of these quadrants is computing exactly the same function, exactly the same structure. Any circuit that has this kind of structure is amenable to this recursion. Another type of circuit is if the circuit is low degree, so particular degree 2, you can always coerce it into this form.
I think we have one more question.
Great.
Does this have any relationship with VSS schemes, because we're implicitly handling malicious dealers? Yeah,
this is a good question. I actually haven't thought about exactly what the relationship is to verifiable secret sharing schemes, but it somehow seems. I don't want to try to give an answer off the cuff, but this is a very good question. So maybe that's it?
There's a meta question, which is, can you clarify what exactly is PRIO?
Okay. Right. I was going to say PRIO is a state of mind, but this is not a very good answer to your question. No, it's so the PRIO system was, I guess, a paper in 2017 from me and Dan that had some of these ideas in it in kind of a rough form that we implemented, and that's actually what is running in Firefox and a bunch of other people have picked up, though the system has evolved over time to include many of the other ideas that I talked about today. So when people say PRIO, sometimes they're talking about this 2017 paper, sometimes they're talking about zero-knowledge proofs on secret shared data, sometimes they're talking about private aggregation, and sometimes they're talking about the artifact that kind of puts all of these things together. Good question.
We have one more question, if you have time.
Yeah, I would love to.
In PRIO, after the servers perform only linear operations to verify the proof, can we let the servers perform more general MPC between them on X without increasing the client's cost?
Yes, absolutely. So what the servers end up with is secret shares of a client's provided vector. And after this, they check the proof. They're guaranteed that the client's vector, the secret shares that they're holding, satisfy some predicate. And then they can do whatever they want with that secret shared information. So one thing that people do is you can have the servers add noise to the client's data such that it provides some kind of differential privacy. Or the servers could do a more general computation, multi-party computation on those values. It turns out, I guess I'll talk about, if I have time, one other application where something more interesting is happening at the servers. But for many of the telemetry applications, it turns out people just want to sum up private values from the client. So that's actually enough for many things.
Okay, I think that's it.
Great. So let me talk about applications, some other applications now. So we talked about private analytics. In the notes, I have some a couple of slides on symmetric private information retrieval, which I'm not going to talk about. What I want to do is talk about what I'll call private heavy hitters. And if I have time, which I probably won't, I'll talk about applications to malicious secure multi-party computation. So, okay. This is an example of kind of what you were just asking about, doing something more interesting with the client's data once the servers had it. So I'll call this private heavy hitters. And this, if you're interested in more information on this stuff, this is from an IEEE security and privacy paper in 2021, and the system, we called it Poplar. So recall in this kind of part one private analytics scheme, the motivating application, we're thinking of a browser vendor that wants to compute the set of popular homepages without learning any individual user's homepage. So if the set of kind of candidate pages that we're talking about is fixed, so the top 10,000, Alexa top 10,000 pages, then we already saw a way to do this. Each client sends a secret shared vector of dimension 10,000 and yeah, so on. But the problem is that if Mozilla doesn't know ahead of time which websites are kind of candidate popular websites, then the scheme that I described doesn't work. So in particular, say that say Mozilla wants to find the popular web pages. From the set of all 256-bit URLs or something, maybe even longer, say like 2000-bit URLs. Yeah, the scheme that we sort of looked at the beginning would require each client, right? The scheme would be each client produces a vector, and this vector has a dimension 2 to the 2048, and then dot, 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 dot. So this clearly doesn't work, right? This is too much. So I want to describe a kind of way for clients to do this using function secret sharing, which Alette talked about, and the malicious secure sort of protecting against malicious clients idea that I just talked about. And there's many other ways to solve this private heavy hitters problem that get sort of different kinds of privacy properties. But since we're talking about FSS and malicious security for secret sharing, I'll present one idea that uses both of these tools. So the setting again is we're going to have the clients, I guess many clients over here, and some number of servers, say 2 servers. And instead of having clients, so what we would have done before is we'd had the clients prepare a vector that's 0 everywhere, except with a 1 in the index corresponding to its the website that's its homepage. And we would have had this vector would be the size, linear in the size of the universe of of potential strings. So this would have been 2 to the 2048. So we're not going to do that now. What we're going to do instead is the following. We're going to have the clients prepare kind of a tree. So think of it like this, where the depth of this tree is n. So this is, say, all this n-bit URLs. And this tree is going to have 1 on the path to the client string. So if the client string is over here, then there's going to be 1s on the path to the client string. This client's input is, this could be the bit representation. So I guess this would be 1, 0 if it's a 2-bit string, and then 0s everywhere else. And the client's going to send secret sharings of the values on each node in this tree to the servers. So the client's going to prepare kind of two secret shared trees. such that their sum is equal to this kind of labeled tree thing, and it's going to send 1 to each of the 2 servers. So there's still a problem here in the sense if this tree has size exponential in the length of the string. So it seems like we haven't really done any work here. But the trick is well, there's 2 tricks. So first trick number 1, is that we can use function secret sharing or distributed point functions to compress the secret sharing at each level of the tree. Yeah. So instead of sending kind of secret shares of each value at the tree, what we can do is we can observe that if you look at the values of these nodes, there's 0 everywhere except 1 at a single location. And this is exactly what distributed point functions give you, as a way to succinctly secret share vectors of this form, exactly this form. Actually, Rahul, did Alette talk about distributed point functions this morning? This was at like 4 a.m., so I didn't see it, but okay, good. So you all are experts on distributed point functions now. So you can imagine, instead of sending these nodes explicitly, the client sends kind of keys for each one per level to each of the 2 servers. And the servers can kind of expand these keys out to get the values of the secret shares of these nodes using distributed point functions. So that's cool. So that's the kind of the first trick. And it turns out we show that if, in addition to using distributed point functions, if we just did it naively, you'd have kind of n keys, 1 per layer, and each key has size lambda n. So this would be kind of lambda n squared communication. You can do something slightly better, and actually each client only sends 1 key, and one DPF key kind of is able to succinctly represent all of the nodes in this tree. So with more cleverness, using something we call an incremental DPF, you can actually reduce the size of this compressed secret sharing to just linear in the depth of this tree. So that's the first trick. The second trick is, once the servers have these secret shared representations of these tree values, how do they find the popular strings? Because still, even though the representations of these things are compressed, the tree itself is exponential in size. So what are they going to do? So this is kind of trick number 2. Number 2, and the trick number 2 is actually not such a deep trick. The trick is just that for any string that's between 0 and n bits long, so I'll write this. The servers can efficiently compute how many clients hold strings beginning with this prefix sigma. So for any prefix, the servers can efficiently compute how many clients hold strings beginning with that prefix. And the way the servers do it is, so the servers are holding kind of these DPF keys, 1 from each client. And what the servers can do, if they want to know how many clients have strings that begin with this prefix, so I guess that begin with prefix 0, because this is the 0 index in the tree. What they can do is they can evaluate their DPF keys to get the value of this node for each of the clients. And then they publish the sum of those shares. And that will tell them how many clients have a string beginning with sigma, for any sigma. So once you do that, once you have that, the servers can actually just use breadth first search to find the popular strings. So where popular means maybe more than 1 million clients hold that string. So what the servers will do, I'll try to draw this give a picture of it. The servers will do is they'll walk down this tree from the root to the leaves, pruning all of the nodes that are unpopular. So the servers will each ask how many clients have strings that begin with the empty string. And maybe the answer is, they'll publish their shares of this value and they'll see the answer is, 37 million or something like this. So I'll say, okay, there must be a popular string, or there could be a popular string under this node. So then the servers will both look at the values of the next level nodes. And they'll say how many clients have strings that begin with 0 and how many clients have strings that begin with 1. And maybe there's only 87 clients that have strings that begin with 0, and there's 36 million something strings that begin with 1. So the servers will say, okay, there's clearly no popular string begins with 0, so we'll prune this side of the tree. We won't even explore it anymore. And we'll continue exploring this right side of the tree. And so they'll kind of walk down the tree looking for the popular strings. And you can convince yourself there cannot be too many popular strings. And thus, the servers will relatively quickly be able to identify all of the popular strings by walking down the tree in this way. So I guess this is the basic idea of how you can kind of use, this is something more complicated than just computing sums over client data. The servers are actually running some kind of more complicated algorithm on the secret shared data, but still sort of relatively simple. So maybe, is there a question about this, or should I keep going?
No.
Okay, cool. So yeah, I hope. Okay, I hope if I lost you completely here, I hope the one thing that you remember is that there's this thing called an incremental DPF that lets you succinctly share kind of values on the nodes of a tree where the tree has a single non-zero path in it. So that's kind of the one primitive to remember. I want to, maybe in the remaining time, so since we're talking about protecting against malicious clients, let me say a couple things about that in this protocol. So protecting against malicious clients. Okay, so the easy part, is going to be an easy part and a not as obvious part. So the easy part is how you ensure that a client didn't send, right? The clients are sending secret sharings of values on this tree. How do we know that a client is not going to send garbage and kind of mess up the entire result? Well, the client's supposed to send, if we remember what this tree looks like. So the client's supposed to be sending secret shares of a tree that has a single non-zero path and is 0 everywhere else. And to test this, the servers can just use this same sketching stuff that we talked about in part 1, where for each layer in the tree, I guess going from top to bottom, the servers use this sketching protocol to check that each client's submission has at most a single 1. So it's all zeros except with a single 1. And this holds all the way down the tree. So if the client is being honest, it should only be sort of voting for one prefix at each level of the tree. So this is kind of the easier part is use sketch verification at each level to make sure that each client only voted once. So cool. Since we already saw sketch verification, we know how to do that. The harder part is actually quite subtle. So if we look at what happens down at the bottom levels of this tree, say this tree is actually much deeper. We have an exponentially large tree here. And at the bottom levels of this tree, the servers won't actually expand all of the nodes down here. And the reason is there's too many nodes to expand. This is an exponentially large tree. So the servers are only actually going to kind of look at the potentially popular nodes in the tree, which might be some subset. So you could worry that a malicious client, could abuse this and say send the server shares of values that are actually one in multiple places, but just not one in multiple places where the servers are looking. And this is kind of a subtle attack that lets one client get more influence than it should have had. And I guess the way that you handle this type of malicious behavior is to kind of modify the standard DPF construction to make it infeasible. So what does that mean? It means that basically, the malicious client can't cook up, two DPF keys such that the client knows the two different places where the key expanded values sum to 1. So in this tree that's defined by this incremental DPF, either the leaves are well formed, like there's only a single non-zero element here, or it's kind of garbage everywhere, but it can't be the case that there's kind of two non-zero leaves here and the client knows where they are. And there's lots I'll put asterisk here because there's kind of some details, but I guess the bottom line is there's a way to handle this, but check out the paper for the details there. So, okay, before I pause for questions, I want to mention also, one application that I would have loved to talk about that I don't have time to talk about, which is using these zero-knowledge proofs on secret shared data to get malicious security in kind of traditional MPC protocols. I have in the notes some details and pointers on that. And the basic idea is that if you have a distributed protocol where people are operating on secret shared data, you can use these proofs to have people prove to each other that they've actually executed the protocol correctly. And if you use these sublinear size zero-knowledge proofs on secret shared data, you can actually do that surprisingly efficiently with very, very little communication. So if you're interested in that, check out the notes and check out the related work I point to there. I think with that, I'll take questions if there's any left.
So one question is that can servers detect clients whose input isn't a path in a tree?
Is whose input is what?
Can servers detect clients whose input isn't a path in the tree?
Is in a path in the tree?
Isn't in a path.
Isn't in a path. Good. Yeah, so you're saying like an example of that would be like this where there's like a 1 over here and 0s over here. Something like this?
Yeah.
Yeah, where so the sketching, this kind of falls under the harder part, where the sketching will not catch that because the sketching is only going to check that you're voting at most once. But this extractable DPF stuff, I should say the name for this is extractable DPF. Will. I guess there's some question about, whether or not this, to what extent in practice this actually matters, right? If a client is only voting once and they vote inconsistently in different parts of the tree, yeah, it kind of messes stuff up a little bit, and we can actually prevent it. But it's not so clear to me that this actually is going to cause a practical problem. But it's definitely a good question, and kind of you have to worry about these details for sure.
So one more question is that like in when you use predicates, do you leak any information regarding about the unpopular strings?
Yes, absolutely. So I didn't get into the formal security definition here is a mess, but there's a bunch of leakage because you're kind of, maybe the simplest way to think about the leakage is you're leaking all of the weights on the popular prefixes if you implement the protocol in the simplest way, which definitely leaks more than strictly the set of the most popular strings. But again, it's not super clear that how important this leakage is. And if you really wanted to defend against it, I think there's kind of more complicated protocols that you could run. I think it just turns out that, when you go to implement the stuff, you're kind of trading off efficiency versus leakage, and I think it's pretty much a subjective choice at that point what you're okay with.
But a follow-up question would be like, how much cost? How costly would it be if you don't want to leak?
Yeah, so I guess
would it be a lot or?
Yeah. So if you want to leak nothing, but the set of strings that say more than 1 million clients have, as far as I know, the only way to get that level of kind of strict security would be, I'll keep it short, but to use kind of general purpose MPC, which would be orders of magnitude more expensive.
Okay.
Okay.
Cool.
Thanks, Henry,
Great.
for two great
Yeah.
talks.
Thanks so much for inviting me.
It's really amazing to see these things, to see the behind the scenes of things that are actually being implemented and incorporated into actual systems. It's amazing to see. So thank you very much for telling us a little bit about it.
Thanks so much.